Welcome to part 3 of our series. Get started with ML agents in Unity. In this episode, we're moving from theory to practice by building our very own ML agents project from scratch. If you've been following along, you now understand the basics of reinforcement learning and how it's implemented in Unity. In this tutorial, we'll bring those concepts to life by creating an agent, which we will later train to perform a simple task. If you haven't watched parts 1 and 2 yet, I highly recommend checking them out first. You'll find the series playlist linked below. Before we dive into the tutorial, I want to let you know that you can download the complete Unity project for this tutorial by joining my Patreon. Access is available through the Script Surveyor tier for just $3 per month, and it includes this project along with other projects I've created. If you're interested, you'll find the link in the description below. Thank you for your support. Alright, let's get on with the tutorial. Fire up Unity Hub and with the Projects tab selected, click the New Project button. Make sure you're using the latest version of Unity 6 and select the Universal 3D template. Now let's give our new project a name. Since it will feature a turtle-like agent, let's call it TurtleAgent. Make note of the location of your new project. You will need to know this later. Now click on the Create Project button. The Unity editor will now create and open your new project. Now that our project has fully loaded, the first step is to import the ML Agents package using the Package Manager. To do this, go to the top menu bar, click Window, and then select Package Manager. In the Package Manager window, select Unity Registry from the left sidebar. Scroll through the list of packages to find ML Agents, then select it, and click the Install button. The package has finished installing. At the time of recording, ML Agents version 3.0 has been installed. You can now close the Package Manager. To check that ML Agents is indeed installed, go to the Project tab and expand the Packages folder. You should see it listed underneath. Let's start building out our scene. The first step is to create a simple environment for our agent to reside in. In the Hierarchy panel, create an empty game object at position 000. Name the game object Environment. Next, let's create a ground plane for our agent to sit on. Right-click the Environment Game object to open the context menu. From this menu, select 3D Object and then Plane. Again, ensure the plane is positioned at 000 and leave its scale at the default of 1. The plane should be parented to the Environment object. Let's rename the plane to Ground. To prevent our agent from falling off this ground plane, we'll add some walls around its edges. Right-click in the Hierarchy view, select 3D Object and then Cube. Next, adjust the cube to fit along one edge of the ground plane. Feel free to copy the transform properties of my cube if you like. Rename the cube to Wall and then create a duplicate of it by pressing Ctrl-D. Adjust the transform properties of the duplicated wall to position it along the opposite side. Let's duplicate the wall again, and let's position it along one of the adjacent edges. We will stretch this wall slightly to make sure it is flush with the other two wall pieces. Go back to the Hierarchy view and duplicate the wall object one last time. Let's move this final wall section into place. Lastly, let's group the wall sections together. In the Hierarchy view, right-click the Environment Game object. From the context menu, select Create Empty and make sure it is positioned at 000. Rename the empty game object to Walls and drag all the wall sections inside it. Later, we'll set up our agent to be penalized for hitting the walls. To visually indicate that walls are something to avoid, we'll apply a red material to them. Go to the Project tab, right-click on the Assets folder. From the context menu, select Create, Folder. Name the new folder, Materials. Inside the Materials folder, create a new material. Let's customize the material. In the Inspector, under Surface Options, change the surface type to Transparent. Go to Surface Inputs and click on the color bar to the right of Base Map. In the Color Picker, create a red color and make it semi-transparent. Let's rename our new red material to wall material. Now let's drag this material onto every wall section. Next, we'll create the game object that will serve as our agent in this environment. It will be a turtle of sorts. In the hierarchy panel, right-click the environment game object and create a cylinder. The cylinder will appear as a child of the environment object. Rename it to turtle. Next, let's adjust the dimensions of the turtle cylinder. In the inspector, change its transform properties to the following values. Let's create a material for our turtle. I'm going to give the turtle a blue color. Let's name the material Turtle Material, and let's apply it to the turtle game object. Okay, we'll want to clearly identify the front of the turtle. To do this, let's add a pair of eyes. I'm just going to rotate the scene view so that the blue Z-axis, representing the turtle's forward direction, points upward on the screen. Next, I'll create two small spheres to serve as the turtle's eyes. I'll position them near the front of the turtle. I am creating an orange material for my eyes here. Let's name the material Eye Material, and let's apply this material to our eyes. Name the eye spheres appropriately, and then parent them to the turtle game object. There is one more object that we require for the scenario that we will be setting up, and that is a goal object. For this, a simple sphere will suffice. Right-click on the environment game object and from the context menu create a sphere. Position the sphere slightly to one side of the turtle and scale it to half its size. As before, we'll create a custom material for this object. This time I'll give the material a green color. Name the material Goal Material and apply it to the Goal game object. Name the sphere simply Goal. Alright, we've created our environment, which makes this a good time to explain exactly what we're going to teach our agent, the turtle, to do. Put simply, we want our turtle to learn how to reach the goal object with minimal fuss. At the start of each episode, the goal will be placed at a random position some distance away from the turtle, and our task is to train the turtle to move towards it efficiently. To make the challenge more interesting, we'll intentionally limit the turtle's movement options. It can only move forward, or turn clockwise or counterclockwise. To achieve this, we'll use Unity's ML Agents framework to train our turtle agent, using reinforcement learning. The turtle will observe its environment by gathering details such as its own position, the goal's position, and its orientation. Based on these observations, it will take discrete actions, either moving forward or turning. We will also define a reward system to guide its learning. The turtle will receive a large positive reward for reaching the goal. It will receive a small penalty for every step it takes, encouraging it to find the shortest path. Additional penalties will be applied if the turtle collides with the walls. Over time, through trial and error, the turtle should learn to navigate its environment efficiently. Okay, before we start coding our turtle agent, we need to set up a few things to ensure that physics and collisions work correctly in our simulation. Select the turtle game object. Go to the inspector, scroll down, and click the Add Component button. Find and select the Rigid Body component. Locate the new rigid body in the inspector. This component enables physics interactions for the turtle, allowing it to collide with the walls, for example. However, we need to limit the effects of physics on the rigid body to ensure the turtle remains level and doesn't flip over during collisions. We will achieve this by applying constraints to the rigid body's rotation, allowing the turtle to rotate only around its y-axis. In the rigid body component, expand the Constraints section. Here, you'll find checkboxes for freezing the rotation on each axis. Check the boxes for both the X and Z axes. There's one thing I forgot to do when we were creating the turtle game object. I forgot to remove the collider components from the eyes. These colliders can sometimes interfere with collision physics in unexpected ways. To prevent this, let's go ahead and remove them now. In the hierarchy view, expand the turtle game object and select both eye objects. In the inspector, locate the sphere collider component and delete it. This will remove the collider from both eye objects. Select the goal object in the hierarchy and then go to the inspector. Find its sphere collider component and check the box for Is Trigger. This setting allows the turtle to move into the goal without a physical collision while still detecting when the goal is reached. In our scripts, we'll need to identify which objects the turtle collides with, or which object has entered the goal's trigger zone. To this end, we'll assign tags to specific objects, such as the walls and goal. Let's set these up now. Go to the top menu bar and select Edit, and then Project Settings. In the Project Settings window, from the left sidebar, select Tags and Layers. In the Tags section, click the plus button to add a new tag. Let's call our first tag Wall. Now let's create a second tag. Call this one Goal. You can now close the Project Settings window. Now let's assign these tags to their respective objects. Select the Goal object. Right at the top of the inspector, you will notice a Tag drop-down menu. Set it to Goal. Next, expand the Wall's game object. Select all the individual wall objects within it. Once again, go to the inspector, and from the Tag drop-down, select Wall. Okay, we are ready to start coding. First of all, let's create a folder to contain all our scripts. Go to the Project tab, and under Assets, create a new folder and name it Scripts. We're now ready to create our first C# script. This will be the main agent class that controls our turtle character. The agent script will define how the turtle behaves in the training environment, specifically how it collects observations, takes actions, and responds to rewards or penalties. Go into your scripts folder. Right-click inside it to bring up the context menu. From here, select Create, and then MonoBehavior Script. Name the script TurtleAgent. Finally, double-click the TurtleAgent script to open it in your code editor. When the script first opens, you should see something like this. First, let's import the required ML agents libraries. Add the following using statements. We've imported 3 key ML agents namespaces here. In addition to the core library, we have imported ML agents actuators. This namespace contains classes related to the agent's actions. We are also using ML agents sensors, which allows the agent to collect observations from the environment. You will notice that the TurtleAgent class inherits from MonoBehavior. Remove this inheritance and replace it with Agent, which is part of the ML Agents framework. This change allows our script to function as a trainable agent and gives us access to built-in ML Agents methods for reinforcement learning. To define the behavior of our TurtleAgent within its environment, we need to override several key methods from the agent class. First, we'll add these methods as empty stubs to outline the structure of our script. This will give you a sense of the overall process before we go back and implement each method in full. Let's just quickly delete the start and update methods. We won't be needing them in this class. The first method we need to override is the Initialize method. Add this code. This Initialize method is called when the agent is first created, allowing us to set up any necessary components or variables. Right now, this just prints Initialize to the console, but soon we'll add important setup logic. Next, let's override the OnEpisodeBegin method. This method plays a crucial role in reinforcement learning. In reinforcement learning, training is typically broken into episodes. An episode is a short session in which the agent attempts to complete its objective. At the start of each episode, we reset the environment to give the agent a fresh start. In ML agents, this reset process is handled in the OnEpisodeBegin method. Now, let's override the CollectObservations method. For reinforcement learning to work, the agent needs to perceive its environment. This is done using the CollectObservations method, which allows us to provide the agent with information about the current state of the environment. Finally, we'll override the OnActionReceived method. Once the agent has collected its observations, the ML agent's backend processes them and then decides on an action. The OnActionReceived method is responsible for executing that action. Okay, that's the basic structure of our TurtleAgent class. Now let's start defining some variables. Add the following 3 lines to the top of the class. A quick heads up. You'll notice that all private variables in this script start with an underscore, for example, _goal. This is a common C# naming convention used to distinguish private fields from public ones. To keep my explanation flowing naturally, I may refer to these fields without the underscore, so I might say goal instead of _goal, but be sure to include the underscore when writing your code. Anyway, let's get back to our script. Notice that each of these variables is marked with the serialize field attribute. This allows them to be visible and editable from the inspector in Unity. The first variable holds a reference to the goal game object in our environment. Since our turtle agent needs to reach this goal, it must know its position. Later, we'll link the goal game object to the goal variable using Unity's inspector. Next, we have move speed and rotation speed, both of which are float variables. Move speed determines how fast the turtle moves forward, and rotation speed controls how quickly the turtle can turn. Now add this line. The renderer variable stores a reference to the turtle's renderer component. We'll use this later to change the turtle's color when it interacts with the environment, such as turning red when it collides with a wall. Finally, add these 2 variables. Current episode and cumulative reward will help us track the training progress of our agent. Current episode keeps count of how many training episodes the turtle has completed. Cumulative reward tracks the total reward the turtle has earned in the current episode. These values will be useful for debugging and monitoring how well our agent is learning. Okay, let's move on to implementing our overridden methods. Go to the Initialize function and add this code. This line retrieves the renderer component attached to the turtle agent and stores it in the renderer variable. The next 2 lines simply initialize current episode and cumulative reward to 0. Next, let's implement the OnEpisodeBegin method. Go to your OnEpisodeBegin method and add the following code. This line increments current episode, keeping track of how many training episodes have been completed. The next line resets cumulative reward to 0, ensuring the turtle agent starts fresh each episode. Following this, the turtle's color is reset to blue, its default color. Here we call the SpawnObjects method, which we are about to implement. This method will reposition the turtle and goal so that each episode starts with a slightly different arrangement. Okay, let's add that SpawnObjects method, and let's take a look at what it does. First, we reset the turtle's position and rotation so that it starts each episode at the center of the environment, facing forward. Next, we determine a random direction and distance for the goal relative to the turtle. Finally, we place the goal at this randomized position. Okay, now let's move on to the CollectObservations method. Add the following code to CollectObservations. Now let's break down what's happening here. Notice that vector sensor is being passed into the method. The vector sensor object serves as a container for the observations we want to provide to our agent. These observations are numeric values, in our case, floats, that describe the current state of the environment, allowing the agent to make informed decisions. Before we continue, it's important to clarify something about the term vector in vector sensor. If you've worked with Unity before, you might assume that vector here refers to a vector 3, which is how Unity represents positions and directions in 3D space. However, in vector sensor, vector actually comes from machine learning terminology, where it refers to an array of numerical values rather than a 3D coordinate system. In reinforcement learning, an agent receives a vector of observations, essentially a list of numbers, that it uses to understand the environment and make decisions. Each number in this vector represents an important aspect of the environment. In our case, these observations include the goal's position, the turtle's position, and its rotation. You may be wondering why I am feeding float values into the vector sensor, rather than simply passing in vector 3 objects directly. While vector sensor does support vector 3, integers, and other types, ML agents ultimately processes observations as a list of floats. This is because the decision-making part of ML agents, the Python backend, uses a neural network, which requires a list of floats as its input. And since we're on the topic of neural networks, let's talk about why we normalize the values we pass into the vector sensor. You may have noticed that we divide the goal and turtle positions by 5 and scale the turtle's rotation to be between -1 and 1. But why do we do this? The reason is that neural networks work best when their inputs fall within a consistent numerical range, typically between -1 and 1. If we were to pass raw position or rotation values into the vector sensor, they could be large numbers. Neural networks struggle to process widely varying scales effectively, which can slow down learning or even make training unstable. By normalizing our values, we ensure that all inputs are in a similar range, making it easier for the neural network to interpret observations and make accurate decisions. Anyway, you can see that we send a total of 5 observations, each a float value, to the training backend or neural network. These values update at every step, allowing our agent to react dynamically. Before we move on, there's something important that I almost forgot to mention. You may have noticed that when we collect observations, we use local position and local rotation, rather than simply position and rotation. But why is that? The reason is that our turtle and goal are inside a parent game object, the environment. This becomes crucial later when we duplicate the environment, to run multiple training instances in parallel. Each environment will have its own local coordinate system. If we were to use position, the global world coordinates of objects in different environments could vary wildly, making learning inconsistent. By using local position, we ensure that the agent only considers its position relative to the environment, which keeps training stable and predictable. Alright, now let's move on to implementing the OnActionReceived method, which will allow the agent to take actions based on these observations. In OnActionReceived, add this code. OnActionReceived is called every step, and it's responsible for handling the actions chosen by the ML agent's backend. Let's take a look at what's happening inside. OnActionReceived takes in a parameter called ActionBuffersActions. This actions variable holds the decision output from the ML agent's backend. Essentially, it tells the agent what action to take at this step. The first line of the method calls MoveAgent, which we haven't added yet. This method will handle executing the turtle's actions, which are limited to a discrete set of moves, such as moving forward or turning. We'll be implementing MoveAgent shortly, and when we do, I'll explain it in more detail. In the second line, we add a small penalty, or negative reward, for every step that the agent takes. The idea is to motivate the agent to reach the goal as quickly as possible, instead of wandering aimlessly. Finally, we update cumulative reward by calling getCumulativeReward. This allows us to keep track of the agent's total reward for the current episode. Now, let's write that MoveAgents method. Add the following code. Let's take a look at how MoveAgent works. The method takes in an action segment parameter which stores the discrete action selected by ML agents. Discrete actions are used when an agent has a limited set of predefined choices at each step. Our turtle can move forward, turn left, turn right, or indeed, decide to do nothing. In our case, the action segment parameter simply contains an integer in the range of 0 to 3, where each number represents a specific movement command. Now it's important to understand where this number comes from. The integer value is produced by the ML agent's decision-making process during training or inference. The ML agent's backend, which includes a neural network model, outputs an integer based on the agent's observations. However, it is up to us to define what each integer value corresponds to in terms of a concrete action. By the way, the range of possible values is defined in the behavior parameters component, which we will set up later. Okay, now that we know where the action integer comes from, let's look at how we translate it into actual movement. We do this using the switch statement here. The switch statement checks the integer value stored in action segment and executes the corresponding movement code. If action is 1, the turtle moves forward. If action is 2, the turtle rotates left. If action is 3, the turtle rotates right. If action is 0, then the switch statement does nothing. No movement code is executed. Now that we've set up movement, the next step is to detect when our turtle reaches the goal. If you remember, the goal object has a collider set to behave as a trigger. This means we can use Unity's trigger system to detect when the turtle enters the goal's trigger zone. Add the following code. This method, OnTriggerEnter, will automatically run whenever our agent enters a trigger collider. The method takes a single parameter, other, which represents the collider of the object that the agent has entered. Here we check whether the other object has the goal tag. If it does, we call the GoalReached method, which we are about to implement. Add this code. Inside this GoalReached method, we perform 3 important actions. First, we give the agent a large positive reward for reaching the goal. We do this by calling the addReward method with a reward of 1. Second, we retrieve the total accumulated reward for this episode. This is done by calling the getCumulativeReward method, which allows us to track the agent's overall performance. Finally, we end the current episode by calling endEpisode. This signals to ML agents that the episode is complete. ML agents will then start a new episode and automatically call the OnEpisodeBegin method, which we overrode earlier to reset the environment. At this point, we've successfully implemented much of the core functionality of our TurtleAgent class. However, since this video is getting quite long, we'll wrap things up here. In the next video, we'll continue improving our agent by implementing penalties for wall collisions. We will then finish setting up our Unity project for training, and finally, we will run the training process itself. If you found this video useful, please like and subscribe. And don't forget to hit the bell icon so you won't miss the next episode. Thanks for watching, and I'll see you in the next video.